Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. In the previous video, we started optimizing the light-culling shader and we already made a small gain in performance. However, we can take this much further by calculating the bounding spheres in C++ instead of in hlsl shader code. Today we are going to finish this optimization and we are also going to do another improvement in order to decrease the number of false positives during light culling. Since we are going to calculate the bounding spheres in C++, we need a buffer where we'll put the results and we'll pass that buffer to the GPU where we read the data in the light-culling shader. In addition, this buffer will contain bounding spheres for both point lights and spotlights. Now we need to repeat everything we do for other buffers in the lightset class. When we add a light, we reserve some extra room in our new buffer. When we change a light's range, we can set the bounding sphere radius to be the same as the range. However, if the light is a spotlight, we use the function to calculate its bounding sphere. This is pretty much the same code as we have in hlsl, but now we'll use directx math to do the calculations. Here we load the spotlight's tip and direction into SIMD registers first. Then, if the angle of penumbra is less than 45 degrees, we use the equation for narrow spotlights. Otherwise, we use the one for wide spotlights. Now we can call this function whenever something happens to a spotlight that would require an update to its bounding sphere. We already called this when a new range is set. Obviously, we should recalculate the bounding sphere when the angle of penumbra changes. And by the way, note that we are calculating the bounding spheres regardless of whether we are using the optimized shader or the original one. This doesn't matter since calculating bounding spheres in C++ doesn't depend on which shader we are using. Next, we update the bounding sphere when we call updateTransform function. This will set the sphere's center, which is the same as the position for point lights, but for spotlights it also depends on spotlight direction. We set the sphere radius when we add light-culling info as well. When we swap lights, we also swap their bounding spheres. That concludes the care and feeding of this new buffer. Next, we need to pass it to the GPU. Therefore, I'm going to add a new buffer enumeration. We don't have to do much in resize buffer function other than setting the buffer name according to its type. In update light buffers, we need to create an additional buffer for bounding spheres. Here we calculate how big the buffer needs to be and then create a buffer with this size together with the other buffers. Then whenever we update the buffer contents, we also update this new buffer. This is done either by copying the entire buffer from the light set or by updating individual entries for lights that have been changed. I believe this is all for managing this new buffer. Let me quickly check if I didn't forget anything. Here we can use this reference instead of accessing the member variable. And of course we need to have an accessor in order to get the buffer address for bounding spheres. Additionally, we need a function that gets the buffer address for a specific frame index. In order to be able to read from the new buffer, we need to add it to the root signature of the light-culling shader. We can add the bounding spheres to the list of buffers and map it to register T2. Now that we know the register number, we can go back to our C++ code and add an SRV root parameter with register number 2. Oh, I see I made a couple of typos in variable names in this function. Let me fix them. Okay, now we can set this new root parameter right before we dispatch the light-culling shader. And in the light-culling shader, we simply read from this buffer instead of calculating the bounding spheres. And since the buffer contains entries for both point lights as well as spotlights, we don't have to check for light type at all. The only thing that we need to do is to transform the sphere center to view space because we do the intersection testing in view space. So now the intersection loop consists of only reading from this buffer, bringing the sphere into view space, and a single call to intersection testing function. Let's run it and see if it works. I'll turn off random lights and enable the heat map. It looks like it worked fine. I'm going to try it with a rotating spotlight with a narrow cone angle. Cool, this works flawlessly. Now let's measure the performance with our new changes. Again, we are in release build using random lights, starting with 64,000 lights. Looks like we went from 15 FPS to 41 FPS. That's a fat 250% improvement. Let's try 4000 lights. That's 381 FPS, which is also more than twice as many frames per second. Unlike with money, I have no problem being greedy when it comes to performance. So let's see if we can get more of those juicy frames out of the GPU. We can see the next opportunity for improvement when we look at the tiles that contain a light, while the light obviously doesn't affect the pixels in those tiles. In this case, the pixel shader is evaluating those lights and will either skip them, which is not good for wave coherency, or do lighting calculations anyway, which results in zero contribution for this light. Either way, it's wasted work. Can we improve this situation? Well, fortunately, we are not the only ones implementing a forward plus renderer, and therefore we can safely assume that there are already a number of proposed solutions to this very problem. First, let's have a look at what's causing this, and then consider possible solutions. Here we've got a tile which extends to a frustum defined by planes A, B, C, and D. As you can see, the light is fully in front of planes A and B. It's also partially in front of planes C and D. Since it's not fully behind any of the four planes, it will pass the intersection test, while it obviously doesn't intersect the frustum. That's why we see a rectangular shape in the heat map instead of a circle-shaped tile grid. As I mentioned, these false positives will waste work in the pixel shader, and the fewer we have of these, the more work we can avoid. Now consider a random frustum with a subfrustum that contains geometry. If any light intersects this volume, it will be included in the list of lights for this frustum. Typically, the difference between the minimum and maximum depth per tile is small compared to the length of the entire frustum. Therefore, we can assume that most subfrustums are also small. We can use this to approximate such a subfrustum with a box that is aligned to the coordinate axis in view space. This is called an axis-aligned bounding box, which can be defined by 2 points. These points can be 2 vertices of the box with a minimum and maximum position with respect to the origin. We can also define this box using its center point and the distance of this point to the walls in each direction. Using this second representation, we can test if a sphere intersects an axis-aligned bounding box. We use this function to get an exact result as to whether or not the sphere intersects the box. The code shown here is from Wicked Engine. The intersection method originates from this presentation by Gareth Thomas, where we find the same code. The intersection method appears to have been invented more than 30 years ago by someone called Arvo. We can have a look at how Wicked Engine uses axis-aligned bounding boxes for intersection testing. Here is the compute shader, and although it's quite a bit different from ours, it follows more or less the same steps. Here we sample from the depth buffer, and it uses wave intrinsic functions to calculate min-max values. I'll discuss this in the next video where we are going to use the same method. Next step would be the intersection testing. However, before doing that, an axis-aligned bounding box is constructed from the 8 vertices of the subfrustum. So they don't use a separate dispatch to compute the grid frustums like we do, it all happens in the light-culling shader. Then we can skip ahead a bit to the intersection testing. As you can see here, we have a branch for each light type where he does construct a bounding sphere for spotlights. Although it looks like it would blow up for wide cone angles. Maybe he's limiting how wide spotlight cones can be, I don't know. Anyway, the sphere AABB intersection function is called in both cases to test if the light should be included or not. I do encourage you to take your time and study this code to understand what's happening. So this is perfect, right? Well, not quite. As you can see, the box is not a tight fit for the subfrustum, which can result in false positives again. However, this is typically much smaller than the ones we get using frustum plane intersection testing. It gets worse when the depth range is larger, or in other words, it gets worse for longer subfrustums. To summarize the pros and cons, sphere AABB intersection yields exact results. It's computationally inexpensive and it's a good approximation for short frustums. However, as we saw in the implementation, we do need to construct a box for each subfrustum, which takes some effort, and it can result in a lot of false positives for longer frustums. All things considered, I think it's a better solution than our current implementation. So we are going to use it in our shader, right? Well, no, we won't. And that's partially because I wanted to try something new. Also, I don't like the fact that we could get a lot of false positives for long frustums. So we are gonna have to invent our own method. At least I doubt that I'm the only one who ever thought of this, but I also haven't found anything like it anywhere, so who knows. Anyway, the method that we are going to use doesn't directly use tiles to construct frustums. Instead, it uses the tile size to construct a grid of circles, which then extend to cones in 3D space. So instead of a grid of frustums, we'll get a grid of cones. Now we need to intersect the bounding spheres with these cones, specifically with a truncated cone frustum with the same depth range as we calculated in the light-culling shader. Wait, but how do we do that? Well, I couldn't find an exact method for sphere-cone intersection testing that is cheap enough to be practical. The best I could find was this one from David Eberle, who has written books on collision detection and game physics, so he definitely knows his geometry stuff. However, this seems too expensive for our use case, so again I have to invent my own method. The bad news is that I'm not as smart as Mr. Eberle. However, the good news is that I am not as smart as Mr. Eberle, and I'd like to exploit this fact to our advantage. Let's have a look at the situation. Here we have a cone and the bounding sphere for a light. The cone has a length equal to the far plane of the camera view frustum, and its base radius in view space is r. We can compute the distance of the sphere's center to the axis of the cone. We can also calculate the cone radius at the point where the sphere's center is projected onto the cone axis. We call this radius lowercase r. We say that the sphere intersects the cone if the distance d is less than the sum of the sphere's radius and the cone radius at the projection point. In order to derive the needed equations, let's consider the cone axis with length d and the sphere. The position vector of the sphere is denoted by s. We start by projecting the sphere's center onto vector d. This is a simple dot product which returns a scalar value multiplied by the direction of d. We can calculate the rejection of sphere's center by subtracting the projection vector from the sphere's center position. The length of the resulting vector is the distance d. Next, we need to calculate the cone radius at point P. We can use similar triangles for this, which states that the ratio of r and distance P is the same as the ratio of cone base radius and the far plane. We can use this to calculate r. Now we have everything we need to determine if the sphere and the cone intersect. However, as I mentioned, I got this result by being a dum-dum, and it means that it's pretty much wrong. At least the math is correct, but the condition for intersection is wrong. And we can see this if we look more closely at the sphere that just touches the cone mantle. You see, the sphere doesn't touch the cone at the point right above the projection of the sphere center. It does so at the point that's perpendicular to the cone's mantle, and the difference is determined by the cone angle. So it's easy to see that the wider the cone is, the more this point deviates from what we had in mind. All is not lost though, because if we replace the word wrong with approximation, we can try and see if it's a good enough approximation. And I think it is for the following reasons. The cone angle for frustums is typically small. Therefore, the error in approximation is also really small. In addition, the cone is already a loose fit for the actual tile frustum, except for the corners. So we would get false positives sooner than false negatives. And even for this corner case, pun totally intended, if the intersection would just fail, it would hardly be noticeable, because it happens at the very limits of the light's range where the intensity is near zero. That's of course unless we are doing some unrealistic lighting where the lights abruptly end. Let's see if we can get this working in our shader. First, we need to construct the grid of frustum cones. For now, instead of creating another type, I'm going to define a frustum to be a cone whenever we are using bounding spheres. In that case, the frustum will contain the direction of the cone and its unit radius. That's the radius of the cone's base divided by the cone's length. In Grid Frustum's shader file, we can use conditional compilation like we did for the light-culling shader. However, this time the shader will be rather different. Here again we return if the current thread is outside of the grid. Otherwise, we calculate the screen space position of a corner of the tile and its center. We would like to use these to determine the direction and radius of the cone in view space. Instead of using screen to view, I'd like to add a new function that can be used to transform vectors to different spaces by providing it with different matrices. So we pass screen space coordinates that are normalized and therefore between 0 and 1, a depth value and the inverse of any of the transform matrices. It then converts the coordinates to clip space and uses the inverse matrix to transform back to view space, world space, or object space. So it's basically the same as these functions, but we have to multiply with inverse view dimensions before calling it. We call this function to transform the corner point and center of the tile to view space. As I mentioned, the unit radius is the radius of the cone base divided by its length. The length of the cone is the same as the far plane. We can get the reciprocal of far plane, that is 1 divided by far plane, from the inverse of the projection matrix. In the previous video, I explained what A, B, C, and D are. So please feel free to convince yourself that C divided by D is indeed the inverse of the far plane. The direction of the cone is simply the unit vector from view space origin to the tile center, and the unit radius is the distance between the tile corner and its center divided by the cone length. Finally, we write the results into the frustum buffer. Next, we can read from this buffer in light-culling shader and do the sphere-cone intersection testing. Obviously, we can't call the old sphere frustum function anymore, so I need to write a new function. Let's add it right here. It takes a frustum cone, a sphere, and minimum and maximum depth values. We return false if the sphere is before the minimum or beyond the maximum depth. Then we calculate the projection of the sphere center onto the cone axis. Subtracting this from the sphere's position will give us the sphere's rejection, which is the vector from the cone's axis towards the sphere's center. Taking the dot product of the rejection with itself will give us the square of the distance from the sphere's center to the cone's axis. We also need the cone radius at the same depth as the sphere center. We can calculate this using similar triangles. We add the sphere's radius to get the maximum distance at which the sphere and the cone just barely touch. Then we say that the sphere and the cone are intersecting if the distance between the sphere's center and the cone's axis is less than this radius. We can now replace the old intersection function with the new one. Looks like we need to exclude some functions that are expecting the frustum to consist of planes. We can put these functions in a pound-if block, so they only get included if we are not using bounding spheres. And here we should use dispatched thread ID. This doesn't look like it's correct. I'm seeing a light that's supposed to be excluded. Let me double check the shader code. Oh, here I made a typo. This should be less than max depth. Awesome! That's more like it. The tiles resemble the shape of the light a lot better now. Although not perfect, it also yields better results for spotlights. Alright, measuring time. .396 FPS for 4000 lights. .44 FPS for 64,000 lights. It's not a big leap, but we still got faster. Also keep in mind that we did this to spare the pixel shader from doing extra work. However, right now our pixel shader is rather simple and cheap. The savings will show up when we have more expensive pixel shaders later on. Note that we didn't have to change anything in the C++ code in order to use cone frustums. Well, I think making the shader run almost 3 times faster is a good result with which we can celebrate the end of this video. In the next video, which is the last part of this episode, we are going to try and squeeze the last drops of GPU juice and see if we can make it even faster. Hopefully you enjoyed watching this video. Feel free to let me know what you think of the engine and the videos so far in the comments below. As always, thank you for joining me and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub so you don't have to type everything over from the video. Plus there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering.